Welcome to this fourth lecture of Engineering Mechanics series, in which we will be discussing about equivalent systems. In the last lecture we have discussed about moments and couples. We have seen the concept of moment and what is the concept of couple. Here we'll be talking about equivalent systems. Now what is equivalent systems? Like for example, if we have a body, let me take a pointer. If we have this body and we have certain point on this body A, we have another point on this body which is a fixed point O. Now the distance from O to A is measured by a position vector R, and at point A we have a force F. Now equivalent system says that if we wanted to transfer this force F to this point O, if we want to transfer this force from point A to point O, we need to add a moment couple on this point O. We can transfer the force also, and we can further have to modify the body, and the modification is to add a moment couple on this point O. So if you see from here to here, what has been done? We have taken this force, moved this force to point O. The direction of the force will remain same, and once we have moved it, since this movement requires an addition of a couple, this is a moment couple which is required due to the action of this movement F. Okay, so if you need to move any point, there are infinite points on this body. So if there is any force vector on that particular point, and you wanted to move that force vector on your desired point, so for that you want to add a moment couple. And now how this is possible? This is very much easily possible if you see this figure. So this was a force we had, and at O we can add a force and we can subtract a force also. This we can always do. We can, at O we can put a force of magnitude F, and we can certainly put down a force of magnitude minus F. So the overall effect at O is negligible. So since the directions are same, the magnitudes are same of all the three forces, these two forces will cancel out and we will only remain with F. Okay, so this is there that we can easily move the force from here to here. But what is the other effect? When we have moved the force from here to here, what is the other effect? We have to add a moment here also. And how the moment is added? So F cannot be simply moved from point O without modifying its action on the body. Attaching equal and opposite force vectors at O produces no net effect on the body. So what we have to do further? The three forces may be replaced by an equivalent force vector and a couple vector, which is called as a force couple system. This is a force and a couple or a moment, and this moment is created due to F times this R, F times this R, and we'll talk more about this here. Remember that whenever the moment couple is added, this should be perpendicular to the line of action of the force. When such a thing is happening, this should be perpendicular to the line of action of the force. Let's see this, how these forces and moments are generated. So moving F from A to a different location O requires the addition of different couple vectors m0. So if you are moving this F to point O, so you have to add a moment couple vector at point O that we have discussed earlier. Okay, m0 O, and this should be perpendicular to the line of action of the force. Now if you wanted to move this system to this location O dash, what you need to do? When you move this system to O dash, these two, both of them should be moving. This movement couple vector, the F will move directly from here to here, but the movement requires a addition of the couple system. Since the force was here, there was no movement here. When we have moved the force from A to O, we have added m naught, and this m naught was the effect of this movement created by F times R. So this was the effect of this movement. Now I wanted to move this O system, both these taken to this O dash. So what will be there? F times this force will be transferred here exactly, and this force will produce F times S, the moment here. So that moment should be added to this moment. And further, if you make different movements, that moment will be added together, and this moment is updated again and again. So the force system is moved like this only, and if you move the moment, you have to add the moment also. That means F times S. So R dash is actually F times S that you have to add. So R cross F was earlier one, this moment was R cross F, and S cross F was this moment. Okay, you add up together, and this moment M dot M MO dash comes up. This MO dash is the moment of two things, the movement from here to here and the movement from here to here. Remember, if we would have moved our force system from A to O dash directly, that thing would not have added. This would not have added. Okay, we would require only this because we have moved from A to O dash directly. So F times R dash would be our moment, couple moment that is required. I hope you are understanding these things. These things will be further cleared as we move forward in our lecture. We'll try to take a simple sample problem. With the help of this, we'll be able to understand different couple systems and moment systems. So this is one kind of a hinge. Okay, this is fixed at this point. These all application problems that we are showing you are real problems. They are actually applied problems, and somewhere they are possibly there in your system around you. Like this is kind of a hanger. You have seen different types of hangers. This is fixed at this certain location, and there are forces existing on this along this direction. You can expect this as a z direction. If this is x direction, this is y, this is z. This is also one direction, 20 lb force, 30 lb forces there, 20. So these are the different forces connected on this hanger. So determine the components of the single couple equivalent system shown as shown in the figure. Determine the components of the single couple equivalent system shown in the figure. So in the figure we have seen there are this forces, this forces, this forces, many forces are there. What we need to do? We need to combine these forces as a single force, single couple equivalent system. So we wanted to move these forces at a particular point. Okay, so what will be our strategy? We will find out the ways to add equal and opposite forces in this particular diagram so that the couple is created. We will produce new couple moments and we will combine them into a single equivalent couple. How we will do that? So what we'll do, if you see this properly, then 30 lb and 30 lb is making a couple, okay, at a distance of 18 inch. This is this direction, this is this direction, same magnitude, making a couple. If you see this is on this axis, 20 lb and 20 lb. They will make a couple, but they are on different axis. So actually they cannot make a couple here. So to make both of them their partners, if we wanted to create their partners, we can add a single force like this, and we can add another force like this. Okay, this will be corresponding to this. Let's say this is 20 and this is also 20. So at a certain point A, I have added this force and this force, both 20. So the overall effect on the system is negligible. But with the help of this, I will be able to make this. See, 20 on this and same axis 20 will make a couple now. And this 20 lb force and 20 lb force will make a couple at a distance of 9 inch. And here this 20 and 20 will make a couple in the distance of 12 inch. So now all these my three system of forces are actually making a couple. So this we will try to follow this strategy, and you can follow such strategies in other problems also. So just wait a moment. So let's say this. Um, um, in this now we will try to make different couples and try to write down the moment equations. So the x component of the moment mx is along the x created by these two couples. Okay, 20 and 20. This is along the x. So no, sorry. Along the x, no, remember that the moment will comes up perpendicular to the plane. So if you see yz plane, just check out yz plane is this plane. Okay, this is your yz plane. On yz plane we have this couple 30 and 30. So the combination of 30 and 30, so 30 times 18 will give me a moment, and this is mx because on by creating this couple, this mx component will be perpendicular to this plane, yz plane. Okay, that's why this is mx. Further, if you see the my is along this. So for my we will be having a plane xz. Okay, this plane we will have xz plane. In xz plane, which couple vectors we have? We have 20 and 20. So the distance between them is 12. So we will take this as this, and the my will be perpendicular to this my. Okay, so this will be this. Mz will be along the z direction. So the couple vector will be on the xy plane. Okay, in the xy plane the vectors will be, which vectors are there? These two vectors are there, 20 and this 20. This 20 and this 20 is in the xy plane. So the distance between them is 9. So we'll calculate the mz. So on the axis you can represent these three components. Since mx is in negative, so this will be in this direction, and this will be, this rotation will be from the right hand rule, and the thumb will point in the direction of the vector, and the fingers will be curling. So use the right hand thumb rule to find out the orientation. In a similar way, my will be along this. This is positive. Mz will be again positive along the z direction. And in terms of component, in terms of ijk, the m vector is like this. So I hope this problem is clear to you. And from this problem, we have seen that from different forces, we can add and subtract a force from a particular point, and we can make different couples. And using the different couples, we will obtain the overall moment component. So this, remember that this vector moment is originating from here, and these are three components, and this will be somewhere like this m, and this m is representing all these forces that are acted on this hanger. Okay, all these forces are represented by this single moment vector. Okay, we'll move forward. So you can try to check out with this also. You can also obtain the components of the equivalent single couple M by computing the sum of the moments of four forces at an arbitrary point. Okay, so you can calculate not by using the couple method also, you can calculate it using the moment, simple moment method also. So for that you have, which point will you select? You try to select point B, because you will have to calculate less, because these two forces will be gone. There is no R here. The R for this and this is 0, so these two will be gone. You will only require the position vector from this to this and this to this. Okay, so you find it out at D, different moments from these two forces, and you will be getting MD like this, and the same moment vector you will be getting. So we can obtain the moment using a couple method also, and using a simple moment method which we have discussed earlier. Now, reduction of the forces to a force couple system. So if there is a body like this and we have a fixed point O, and this point, this point and this point is at a distance of R1, R2 and R3. A1, A2, A3 is at a distance of R1, R2, R3. So if we will move, we would like to move F1 to O, F2 to O and F3 to O. We will like to move all these three systems to O. What is required? We will add, or we will put all these three systems to O without changing their direction, and we will add a couple to O, and the couple is added perpendicular to each forces. F1 perpendicular to this, M1 is added, perpendicular to F2, M2 is added, perpendicular to F3, M3 is added, like this in this figure. Okay, so we have various moments M1, M2 and M3 and different forces. So now it is important that even these three forces and couple systems can be equivalently added together. So all the forces represents this R resultant, and all the moments represents this overall summation moment MOR. Okay, something very similar that I have told you. But the important thing you must remember the important thing which we have discussed earlier also. We have moved the system this to this, this to this, this to this, and added each, representing each force, we have added a moment corresponding to this. Okay, but if we would like to transfer this to a different point, okay, the force will remain same. Further, the force R will remain same. However, the moment will be changed or updated from this to R times this also. So you have to add R times this distance to this moment. This is what is being done here. This was the original distance, this was the original moment, and S times, when we have moved the force couple system to this point, what we have done, we have S times R, we have also added the moment to the original moment. So the moment is updated. And if you would like to move this point from this point to this point, again, your overall representative force will be same, resultant force will be same, however the moment will be updated. Okay. Further reduction of system of forces, this can be done also. So remember that if the forces and resultant couples are mutually perpendicular, as I told you, they should be mutually perpendicular. They can be replaced by a single force acting along a new line of action. So this can be done only when the forces are concurrent, like this, three forces are coplanar on the same plane, or the forces are parallel. So this will be told to you in the next slide. Like for example, system of coplanar forces reduced to a force couple system at R, M0, that is mutually perpendicular. So this M0 is perpendicular to this R, but since this is 2D, so you are not able to see the moment being perpendicular. Only the orientation of the moment is same. This R represents all the three forces acting on this body. then they are saying that this R and M, the system can be reduced to a single force by moving the line of action of R until its moment about O becomes MOR. What does that mean? What does that mean? That means that this system, this R can be further, this R and M at this point. This R and M is at this point, but this is acting on this body. So on this body we can reduce this to further to R. How we can reduce? To a single force R by moving the line of action of R. Line of action of R to another point by MOR. So this is done like this in terms of rectangular coordinate systems. So you can move the location from that certain point to another point, and that location will be MOR by R. Okay, we'll talk more about this in some numerical problems. So you have further, if there are many forces about a certain point, you can reduce that to a single force. Okay, this is a sample problem where we have one kind of a beam, and using this we'll try to find out the moments and couples and try to reduce them into a single forces. We have been asked to find out the equivalent force couple system at A. At A we'll find out equivalent force couple system, and at B also we need to find out the equivalent force couple system and find out a single resultant force. So whatever we have done till now, whatever we have learned till now, we will apply them in this problem. So listen and see this problem very carefully. Okay, this is a system. You might be given some other system in the exams, but the concept and the overall procedure will be same. So an equivalent force couple system at A. So what needs to be done? We will like to transfer all the forces to A. That will be done like this. So first of all, we will find out all the resultant of the forces at A. What is the resultant? Let's say that this is along Y, so this will be J component and X will be the distance component. Okay, so this is positive, downward is negative. Okay, so this is sum up all these forces. So 150, since this is in the J direction only, so we will have only J vector, add up together and we will be getting the resultant vector in this form. Now we'll make this body again and we will add up the resultant vector. Okay, now we need to find out the moment. The resultant is very simple to obtain. We have added all the forces together, the force component together, and what will be the moment? The moment will be this 150 will not make any moment because this is 0 at this. This 60, when we transfer this to this, when we transfer this to this or add minus 600 to this, so the effect of transfer of these forces at A actually added a moment also. So when we have transferred these forces at A, we have added them together and the moment will be added up together. So 150 will not produce any moment because the R is 0. 600 times this will be this. Okay, 100 times this distance and 250 times this distance. Add up together, sum up together, and you will be having a moment. So this will be moment at A. All these directions, all these things, just take care of yourself. I have told you that clockwise will be negative, anti-clockwise will be positive. Told you earlier. Now I have to, the problem says that equivalent force couple system at B. So I have already obtained the equivalent force system at A. So I will transfer this to B. And we know that when we will transfer this to B, what is required? We can transfer force as it is We can transfer force as it is, and to transfer the moment we require the addition of, when we transfer this force on this, so force will be transferred directly and the moment will be updated by force times this. So this moment plus force times this will be added in that moment also. Okay, how this is done, just see. So this was our earlier A part. Okay, in the B part I have transferred the force here. So the transferring of the force requiring the updating of the moment. So earlier moment was this. This will be updated by RBA. RBA is this. Okay. Remember that we are calculating distance from B to A. So distance will be negative. We are calculating distance from B to A. RBA. B to A. Okay. So this moment the effect is 2880. Okay. So this moment is being updated and put it here. So the overall moment will be plus 1000 Newton meter, and this will be perpendicular to the plane. Okay, so the overall XY system will be 600 newtons, this downward force, and 1000 Newton meter will be a moment in the clockwise direction. Okay, so the moment is updated here. So the overall moment and forces is being shown to you here. Okay, further, what is being said in the third part of the question is we need to find out a single force or resultant system at some location on this beam AB. So to do that, what we need to know that the overall resultant force is R. Okay, so the R may be anywhere on this beam AB. Let's say the overall R is at a distance of x. So x times R will be a moment, and what will be the moment? The moment at A. So the moment at A is, because we are taking the distance from A. So we know that R times x is moment at A. So this is the moment at A. So with the help of this we'll be able to find out the distance. So this R will be an equivalent R, a single force required at this beam AB at a distance of 3.13 meter from A. Okay, so in this way we can find out the location of the resultant force also, and we can reduce our overall forces on the system to an equivalent single force. So I hope you would have understood this problem carefully. Further, we'll try to solve one more problem. In this is kind of a bracket, and this is a very practical problem actually. You might have seen such brackets in your electrical distribution systems where your main line is coming. So these types of socket used to act as a live wire or a neutral wire sometimes, and from the live wire we have taken the supply from, this may be going towards your bedroom, this may be going towards um, your another room, kitchen, or somewhere else, and here the main power supply is there and it is connected. So this is the kind of a bracket. I'm assuming that such type of things happening. So this is kind of a bracket which is fixed at this location, and here the wires are moving towards your room or your bathroom or your kitchen or somewhere like this. So the movement of the wire can be represented like this. Since the wire is creating a tension, so this is exactly a force of 100 newtons. Similarly, another wire. So this is a 3D problem. It's important to notice that this is a 3D problem. This is orienting, this is in the XZ plane only, but at a 45 degrees to both the axes. This is in the YX plane. Okay, this vector is in the YX plane. So this will create a moment in the Z direction. This is in the which plane? ZX plane. So this will create a moment in the Y direction, and this is also in the zx plane, creating a moment in the z direction, y direction, sorry. So we have three forces, all the coordinates are giving. What is required? Replace the forces with an equivalent force couple system at A. So we have to find out the equivalent force couple system at A. What is to be done? Transfer these forces here, transfer all the forces here, create a equal, as a resultant of them, create a moments also. Okay, and find out an equivalent force couple system at this point. We do not need to further reduce it, we just need to find out the equivalent force couple system at A. So to find out the equivalent force couple system, we have to obtain the, add up all the forces together at A, this is one thing, and transfer these forces to this, and the transfer will take place, will add up a moment here. The transfer of this to this will add up a moment here, and the calculation of that moment is required, and the calculation will be position vector going from here to here, position vector going from here to here, position vector going from here to here. Okay, let's see how this is done. Overall, first of all, we will find out the position vectors. So we need to get it at A, so we will find out the position vector RBA. To just calculate the position vector, I have told you the procedure. RCA, calculate the position vector in that case also. RDA, this will be the 3D one, so calculate the position vector carefully. RDA, this will be in the other plane. Which plane? Y x plane. So I and j is required. This is in this plane, xz plane, so I and k is there. Okay, now we have obtained all the position vectors, but one thing is required till now. We know the forces here, we know the forces here, and we know the forces here, but the coordinates or the angle is not known here. Okay, so FB as a vector is required. We need to find out these forces as a 3D vector. So for that, like for example FC, this force, we can do it easily. 1000, x component will be 1000 cos 45, and x component is 1000 cos 45, and through this angle z component is cos 45 here also. In this case, the x and y component will be there, cos 60, cos 30, 200 cos 60, 200 cos 30. This will be the x and y component. So with this we can obtain FC and FD. But how to obtain FB? Because we do not have any angles here. So to do that, we need to find out the approach using a unit vector. So obtain a unit vector along this axis. We know the unit vector is obtained by vector divided by the magnitude of the vector. So the vector here is, the coordinate of this point E is given. These three things are given, the coordinates are given. Okay, now we need to find out the vector. So the vector will be REB. REB will be 150 is x. So 150, but the overall axis here, the x is originating from here. So 150 minus 75. So this will be 75. Okay, in this case, J means y. So this is from this y is how much? Minus 100. So minus 100 and minus 50. This will be minus 150. Okay, and in k you find out the k for yourself. Okay, so k is from this 50 and 100. So 50 minus 100, sorry, 100 minus 50. So this will give you plus 50. Okay, find out the magnitude, and the unit vector is obtained. Then now multiply the unit vector with the magnitude, you will be obtaining the force vector. So try to do it by yourself. Okay, the more you do it by yourself on pen and paper, you'll be able to understand much better. further add up all the resultant forces together in I, J and K coordinates. The components add up together and find out the resultant vector, and the resultant moment is obtained like this. Just multiply it the way we know, the usual way of multiplying the position vector with the force vector. So we'll be able to obtain the determinants by multiplying them together. Try to do it by yourself and try to do it 2 or 3 times so that you will be able to understand it much better. Okay, so in this way we can obtain and calculate the resultant forces, resultant moment, and we can transfer the different forces to a particular point. These things are known as equivalent systems. Now, so this is a typical three-dimensional problem that we have solved, and I hope that you would have understood this clearly, especially this problem, especially this 3D problem. This is very important problem. So in this problem we have approached various things. We have approached the unit vector method also. We have seen how to find out the position vectors, okay, and how to replace the forces and couple systems to a particular point. I hope this video would be informative to you, would be benefited to you, and I hope to meet you in the next video. Thank you.